Hey guys, so for the homework help video, there's a lesson I have to just go through real quickly because there's some definitions that I didn't cover explicitly in the previous videos and we'll need one for one of the homework problems that I'm going to do. So let's just cover real quickly what are called type 1 errors, type 2 errors, and power. So just as a review, consider the following hypothesis test. So we had some research question that asked, is the true mean greater than 10? So clearly we see our alternative hypothesis right here follows a yes answer to the research question. And our null hypothesis is the opposite. So our alternative is yes, mu is greater than 10. The null hypothesis is no, mu is less than or equal to 10. From that, we can see that our null mean is 10 right here. So that mu naught number is the number that divides the world of the null and alternative hypothesis. And so now let's go over these definitions real quickly. So it's always possible to get the wrong answer when we do a hypothesis test. Only one of these two hypotheses can be correct. They cannot both be correct at the same time. So a type 1 error would be if we rejected a true null hypothesis. So that would be an error because we don't want to reject something that's true. The probability of this occurring is actually the p-value. So that comes out of our data analysis. We find the p-value and we use that. And in fact, that's how we decide. We say we get a p-value of 2%, which is less than an alpha of 5%. Then we'd say I reject the null hypothesis because the probability of me being wrong by doing so is only 2%, and I set myself a threshold of 5%. I came in less than the threshold, so I'll go ahead and reject the null. So alpha is actually the threshold you set for yourself of what probability of a type 1 error you'll be willing to accept. Now, a type 2 error is the opposite type of an error. That would be if we accepted a false null hypothesis. Okay? So the probability of a type 2 error is a little bit more complicated. It's going to be a function of the sample size, the standard error of the estimate, and it's also going to be a thing or related to the distance between the true mean, because notice that if the null hypothesis is false, then we want to reject this. Well, if the truth were like, oh, actually mu is 1,000,000, then that would make it much less likely that we would accept this hypothesis. It's very likely that we would end up accepting the null. On the other hand, if the truth was that mu was 10.001, well, the alternative is true, but it's going to be hard to see that in the data because the null, 10, and 10.001 are really close together. So it's going to be hard to pick up that up in the data. And that's why the probability of a type 2 error right here depends on the distance between mu and mu naught. An example of that's going to come up in the homework problem we do in a second. Now, what's called the power of a test is the probability of not making a type 2 error. So if you remember from your last class, the probability of not something happening is simply 1 minus the probability of that thing happening. So once we know the probability of a type 2 error, it's easy to calculate the power by just taking 1 minus that. So just by way of example really quick, suppose we had that same set of hypotheses up here. So mu is less than or equal to 10, mu is greater than 10 for the alternative, that again, mu naught, the null mean is 10. So suppose that the truth is that mu equals 15. So the alternative hypothesis is true. This means that it's possible for us to go get data and make a type 2 error. Notice it's impossible for us to make a type 1 error here because part of a type 1 error is rejecting a true null, Well, by assuming that the truth is that mu equals 15, that is assuming that the alternative is in fact true. Now you might be thinking, well, if I already know what the truth is, why would I ever do this? This might come up in an example like maybe your company will get a fine if some chemical measurement is above 15. Well, if you can't test all your product and you want to make a sample, you might want to do this type of exercise thinking, okay, well, what if in truth we're above the threshold? What is the probability that we're going to pick that up in the data? And so you could imagine doing this for different levels of true means right here. So we could try 13, 15, 20, and calculate the probability of making a type 2 error in those different circumstances. Now let's think about mechanically what's happening here. So based on this set of hypotheses, we have this red diagram centered at 10, that's mu naught, so that's the null distribution. Oops. That's the null distribution. But we've been told in this problem that the truth is that it's centered at 15. So the true distribution is represented by the blue bell curve. That's where our data actually is coming from. Even though we're doing this hypothesis test to ask if it's different than 10 or if it's greater than 10, we've also been told in this example that the truth is, in fact, is yes, it is greater than 10. It's 15. So we know from our experience with hypothesis tests that there will be some critical threshold right here that I'll call the critical mean. And if we land to the right of that number, so anywhere in this direction, we are going to reject the null hypothesis, and that will be the correct decision. On the other hand, if we land to this side of that line, we will accept the null hypothesis, but that would be an error in this case, right? Because the truth is that the null hypothesis is indeed greater than 10. So what are the probabilities of these events occurring? Well, first of all, the probability that we're going to land to the left of this black critical mean line is represented by the area under the true distribution. So right here, if I shade this area under this blue curve represents the probability of landing in that area if the blue curve is the true distribution. So that right there, for this problem, represents the probability of a type 2 error. Now we could calculate the power directly from this. Power equals 1 minus the probability of a type 2 error. Or from the graph, we can see, well, what's the opposite of that area? Let's do green. This over here represents the probability that we'll land to the right of the black line over here. And if we land in that area, we'll reject the null hypothesis. We will not make a type 2 error. And so this area right here represents the power of the test. So you can always take your true distribution and divide its areas between the probability of a type 2 error and the power of the test. Now for these types of problems, I cannot do these problems without taking out a piece of scratch paper and drawing it out to figure out what's going on. So I'm going to show you this stuff in Excel, but I'll refer back to this as we're doing it. Now in Excel, actually, in our problem, we are going to have a two-tailed test. So that would look something like H naught HA mu equals, let's say, 7. Mu does not equal 7. And say our mu naught then obviously is 7. And let's say our true mu is going to be given for these types of problems. So we'll say it's 9. Now this is a two-tailed test. So I'll have my null distribution and my true distribution to the right because the truth is greater than the null, right? This is 7. That's mu naught. This is 9. That's the true mu. And so now we're going to have a two-tailed test. In that one-tailed test, maybe our critical mean was right here. Well, what's going to happen in a two-tailed test is sigma has to be divided between both tails. So we'll have to remember to push this a little bit this way when we do our two-tailed test. Because remember, like if this is a one-tailed test, this area right here would be 5% if alpha was 0.05. But down here, this area, when we pushed it out, needs to only be 2.5% because we also need to stick 2.5% in this tail. Okay? So that's going to be a little bit something that's different. You'd also have to think about this a little bit differently if your true mu. What if your true mu in this example was actually mu equals 5? Then our true distribution would be over here somewhere. And that's going to affect how we're looking at these numbers. Because remember, like in Excel, the formulas always give us the area to the left. So we need to think about that issue when we're doing any types of problems related to type 2 errors or power. And so I'll do an example of this when we get into Excel in a second. All right, here we are in the Mind Tap homework, and I was going to show you 2 problems from Chapter 9 assignment and 2 problems from Chapter 10 to get you rolling on those. And I've tried to always pick a couple that should help you with other problems broadly. So in Chapter 9, I'm going to click in here. I'm going to go to Reading Review Assignments, Chapter 9 assignment. And let's start with Chapter 9 assignment number 5. So 5 right here tells us that the mean hourly wage for employees in goods producing industries is currently 24.57. Suppose we take a sample of employees from the manufacturing industry to see if the mean hourly wage differs from the reported mean of 24.57 for the goods producing industries. So they're taking like a subset from goods producing called manufacturing and comparing that to wages in all of the goods producing industries to find out how manufacturing wages relate to that. Now, I read differs from loudly because that's kind of our key word that tells us how to set up the hypotheses. So from that, if the answer was yes, so if I was doing this notes, I'd write mu equals true population average manufacturing wage. So let's jump to the alternative hypothesis. I always think that is easier to do first. So if the answer was yes, it does differ from 24.57, then that would be number 1 right here. The alternative hypothesis, mu does not equal, another way of saying differs from 24.57. So that's going to be number 1. The null hypothesis is just going to be the opposite. It's going to be 1 because that says the null is that mu equals, does not differ from 24.57. So that part's just about knowing how to get those hypotheses right. Now, next it says, suppose a sample of 30 employees from the manufacturing industry showed a sample mean of 23.89 per hour. Assume a population standard deviation of $2.4 per hour and compute the p-value. Round your answer to 4 decimal places. So I've got my Excel calculator ready to go here. I was actually going to clear these out and show you guys where all these numbers are coming from when we get there. So here's Chapter 9, Assignment 5. I've just labeled the tabs, and when you guys get this spreadsheet, you'll just have the tabs labeled by assignment and question number. So in this one, I've just listed out. I always kind of like to read through the problem first. And we wouldn't know this part yet, so I'll type that later. So I'm just listing out what I'm going to need, and then it's just like filling out a puzzle, right? So what do I need for these problems? Well, I need a sample size. It tells us a sample of 30 employees, so I'll just type 30 there. It tells us X bar from that sample was 23.89. So in our data, we've observed a manufacturing sample average wage of 23.89. Mu naught, that's that mu with the little 0 next to it, how I write it in the notes. So that's our, like in this hypothesis, the mu naught was 10 because it's the number that divides between the two hypotheses. Well, in this one, it's 24.57. So there we go. Sigma, they tell us assume a population standard deviation of $2.4, so 2.4. Now we're ready to create a z statistic because we have x bar minus mu over the standard error. So I can do equals, open parentheses, x bar minus mu naught divided by, now we need the standard error, so that's going to be open parentheses sigma divided by the square root of n, because that's just our formula for the standard error of x bar, right? So now my z statistic is minus 1.55. So I landed to the left of 0 because I got an x bar that was less than the null hypothesis, so it makes sense that this is a negative number. Now the question is that negative enough to give us a rejection of the null hypothesis? So let's first just find the probability to the left of that will be one of our tails equals norm dot dist minus 1.551886. Actually, why did I type that out? That was dumb. I'll just click on this, comma, 0, 1, because this is a z statistic from a standard normal distribution with an expected value of 0 and a standard deviation of 1, and true. So that's 0.060344, but that's actually not the p-value in this case because this is a two-tailed test from the equals and the not equals. We have to double the probability. We need the probability of the left to the left of negative 1.55 plus the probability to the right of positive 1.55. But it's a symmetric distribution, so another way to do that is to do 2 times this probability. So you always have to kind of remember to do that when you're doing a two-tailed test. Now, one other thing I wanted to show you, and I showed you this in a past video, but here we converted to a z statistic and put it in this normal distribution function. We can always do, once you're more used to using Excel, this will accept any type of normal distribution. So notice if I put in my particular x bar, so not converted to a z statistic, the mean, the null mean, 24.57, comma, the standard deviation, that's the standard deviation of x bar, which is the standard error. So there I'll want sigma divided by the square root of n, comma, true. And notice that actually gives me the same probability because Excel is doing this extra step for you of converting this stuff to a z distribution when you just plug it in straight away. And of course, if we do 2 times that, we'd get the same number. So that's 0.12069. So the p-value, round your answer to 4 decimal places, 0.1207, right? 0.1207, because we want to make sure our rounding is correct. Now with alpha equals 0.05 as the level of significance, what is your conclusion? Well, our p-value is greater than alpha. And when we're doing the p-value approach, we accept the null hypothesis when our p-value is greater than alpha. This is the probability of us getting a type 1 error, 12% approximately. But the threshold, the maximum threshold we said we'd reject at is a 5% probability of a type 1 error. That's how you can think of as alpha. But we got a higher probability than that. So we're going to go ahead and say the p-value is greater than alpha. So we do not reject the null hypothesis. We cannot conclude that the population mean hourly wage for manufacturing workers differs significantly from, because that's from that keyword from the question. And now it said repeat the preceding hypothesis test using the critical value approach. Round your answer to 2 decimal places. So the critical value approach is when we compare our z statistic to the critical value. So let's see, z critical will be equals norm dot inverse. It's a two-tailed test, so the probability 0.025 to the left, or we could do 0.975 if we wanted the positive number, but since this is a negative, I'll go ahead and do the negative version. 0, 1, and that's a negative 1.95. So thinking about these diagrams, we didn't land far enough away. We only landed 1.55 standard errors away from the null hypothesis, but in order to reject the null hypothesis, we would have needed to land 1.96 standard errors away. So here it wants 2 decimals, negative 1 point. This rounds to 1.55. And we cannot reject HO. These p-value approach and critical value approach will always give you the same conclusion. And it looks like those calculations worked out. Green means good to go. So what are we doing next? Chapter 9, assignment 9 here. So let's skip ahead to problem 9. This is the one where we're going to be talking about power, which is why I had to go over that lesson, and the probability of type 2 errors. So a production line operation is testing for filling weight accuracy using the following hypotheses. So the filling weight, the true average filling weight will be mu. So the null is that mu equals 16, and that's good. Filling is okay, keep running. The alternative is that mu does not equal 16. So filling is off of the standard, stop and adjust the machine. So this is an example where you might think, well, as long as the true mu is between, say, 15.9 and 16.1, we're good to go. But if the filling weight is 16.5 or more, it'll break our machine. But we don't have time to test every single one, so we'll take a sample and figure out the probability we'd be able to pick up a 16.5 problem. So if the mu is actually greater than 16.5, maybe that's the threshold where the overfilling becomes a problem for the machinery. So that's kind of an example where you'd come up with this situation where we have a hypothesis test where we are centered at the value we want, but we say, well, if this is the true value, that's going to be a problem. So let's see if we'll be able to pick that up using hypothesis tests. So these are the null and alternative, and then it tells us the sample size is 39, population standard deviation 0.7, alpha equals 0.05. So a type 2 error occurs when we accept a null hypothesis that is not true. So concluding that the mean filling weight is not 16 ounces when it actually is, that's actually a type 1 error. But the second one says concluding that the mean filling weight is 16 ounces when it actually is not. That would be a type 2 error, so that's the one we want there. So what is the probability of making a type 2 error when the machine is overfilling by 0.5 ounces? So that's saying, so our mu naught from the hypothesis test is 16. That's just the number that divides the null and alternative hypothesis. N is going to be 39. Sigma they give us as 0.7. Why are you bolding me? Why are you bolding me, dude? Alpha, 0.05. Actual mu, so remember, this is the mu from the hypothesis test. But then the question says, what is the probability of making a type 2 error when the machine is actually overfilling by 0.5? Well, overfilling by 0.5 means 16.5. Okay? So the critical value associated with our hypothesis test, we're doing a two-tailed hypothesis test with sigma 0.5. So the critical value, and this is going to be a z, because we know the population standard deviation, sigma up here, dot inverse. So norm dot inverse, there's we put in a probability, so 0.975, comma, 0, comma 1. That's our critical value. We need to land 1.96 standard errors away to reject the null hypothesis. Notice that I could take 16 plus my critical value multiplied by how many standard errors I need to go above the null to reject it, times, well, what is my actual standard error? It's sigma divided by the square root of n. That's my standard error, right? So that says, because remember here I didn't convert, so we were working with 10 and 15, which are from the hypotheses. I never converted to a z. So what I just did here is I converted to a z just to get the critical value. But then I turned that back into these filling weight numbers by adding basically a margin of error above to say, well, when would I land far enough away to reject the null hypothesis? Another way to do that would be to do norm dot inverse probability 0.975, because I just want 2.5% in that upper tail. Mean is 16 now. Standard deviation is sigma divided by the square root of 39. And those numbers are the same number. So Excel just did this extra conversion for me. So I did a z statistic and converted it back into these weights by multiplying by the standard error using sigma over the square root of n. But you could also just do it from the actual distribution. Now you can't do that with t. T, you would have to do it this way, where I converted to t and then back, because t doesn't give you the general distributions because they depend on the sample size, those degrees of freedom. So what is the probability of a type 2 error? Well, so here we're sitting in a problem just like this, but in this problem we have 16 and 16.5. And I figured out my critical mean at 16.22 right here. So the question is, so my true distribution, the blue one, is sitting over 16.5. The probability that I don't get past that critical mean is the probability I land to the left. So this is our null distribution at 16. If I land anywhere to the left of this, I'm going to fail to reject the null hypothesis, and that will be a type 2 error. So if I land to the left of this number in the real distribution, then I'm going to have a type 2 error. So the way to do this is say, okay, let's figure out the z value of that. So norm, or sorry, no, I'm doing a z statistic. So this value minus 16.5, because now I'm looking at the true distribution. It's actually filling at 16.5, divided by sigma divided by the square root of n. So that says that I'd need to land 2.5 standard errors to the left of the truth to be to the left of this line and make a type 2 error. So the probability of that occurring is equals norm dot dist. I'm looking at a probability to the left, so it's fine to just use that number right there, comma 0, comma 1, comma true. So there's my probability of landing to the left of that line. And remember, that's the probability of a type 2 error. And notice that once we know the probability of a type 2 error, the power, so that's the pink area I just calculated for this problem with 16 and 16.5. That's this number right here, 0.006197. The power is the green area. This is 1 minus the pink area. So this is a pretty powerful test. There's a 99.38% chance that we will not make a type 2 error. So going back over here, probability of a type 2 error when the machine is filling 4 decimal places is going to be 0.0062. The power of the statistical test is 1 minus that, 0.9938. And now real quickly, remember when we talked about this type 2 error except false. So the probability is a function of the distance between the null mean and the true mean right here. Well, the power then also must be a function of the difference between the true and the null mean. So in this hypothesis test, notice that if the truth was really close to 16, we would have a very low probability of rejecting the null hypothesis because the truth is really close to the null hypothesis. On the other hand, as the truth, so possible values of mu, if the truth gets farther away in either direction, then the probability of us rejecting the null hypothesis increases. So the power increases. So very low power when we're close, high power when we're far away. That's what this graph represents. This is the wrong graph because it says power, but if this says probability of a type 2 error, it would actually look like this. The probability of not rejecting the null hypothesis is very high when we're close to the truth, but becomes lower as we're getting farther from the truth. So these two graphs are just inverses because probability of type 2 error and power are inverses. So the answer to this one will be the power curve B right here. So what information does the power curve contain for the production manager? The probability of failing to reject the null hypothesis for various mean filling weights. So let's check that, cross our fingers. Ah! Oh yeah, probability of rejecting. Duh. So it's the probability of rejecting the null, because we want to reject the null hypothesis in this case. So that's more powerful when we can. So this is the probability of rejecting the false null as the true value gets farther away from that null hypothesis. All right, so those are the calculations for that one. Thinking about power and probability of type 2 errors is a little bit complicated, so it's definitely worth taking your time and just setting back and actually thinking about it to understand what's going on. I'll probably ask 1 or 2 questions on the Canvas quiz about power and or probability of type 2 errors. So now let's jump into chapter 10, assignment. So I was going to do chapter 10, number 4. So in this one, they give us some data. The average annual cost, including tuition fees, public colleges versus private. At private colleges, the average annual cost is equal to about 60% of the typical family's income. The following random samples show the annual cost of attending private and public colleges. Data are in thousands of dollars. So if you click on this data file, it'll actually give you the data right here. I just copied and pasted it, so that's the data you'll get. And then what I did is I started just filling out the stuff I'll need to answer this question. Okay. So first it asks for just give us the averages and the standard deviations for these two different samples. So X bar 1 is private and X bar 2 is public, which is not super obvious, but I just figured it out. They say private first and public second, so I guess then that ended up being the right way to do it. So I've labeled my spreadsheet here. Here's my data. I wrote X bar PR for private, so the sample average from the private colleges. So we just type average, those numbers. So that's 42,500 per year. Equals average now for the public colleges is 22,300 because those numbers are in thousands of dollars. So Weber State's obviously a sweet deal if those are real averages. So SPR, the sample standard deviation, STDEV.S for sample of private, and STDEV.S for public. Woo! Where you go? Where are you going? Right there. So there's our standard deviations. We also want sample sizes equals count. So we have 10 private colleges and equals count. And we have, no. Yep. Woo! 12 public. You don't want to be counting to 12, bro. So there's some critical information. X bar 1 for 2.50 because it says 2 decimal places, bro. 22.30 down here, 22.30. S1, I called it SPR for our 6.98er. And we got S2 is 4.53 4.53 What is the point estimate of the difference between the two population means? Round your answer to 1 decimal place. Well, I could put D bar right here because that's my estimate bar. D for difference. D bar equals this guy minus this guy. That's 20.20. 1 decimal place, so it's actually 20.2. They're messing with you on the decimal places just like I did on the quiz. That's fun. Interpret this value in terms of the annual cost of attending private and public colleges. 20200. That's that number in thousands. Or no, that's the number in thousands. That's the number in oneses, right? $20,200 is what that number represents. Develop a 95% confidence interval of the difference between the annual costs of attending private and public colleges. Round your answer to hundreds. All right. Well, what do we need when we do confidence intervals? We need our specific standard error. Down here, we're going to need how many standard errors we need to go. That'll give us our margin of error. We'll subtract it. We'll add it. We'll have an answer. SE. So our standard error when we're doing these differences is something like SQRT, open parentheses, S squared for the variance. So this guy squared divided by N plus S2 squared for the second sample squared divided by the N for that sample, close parentheses, enter, 2.57. Now this is where it gets hectic. So we have to use this horrible formula for degrees of freedom, which I brought up in the past that in a video at some point. So I'm going to go and find, so we're in chapter 10. And you can always have your book open. The exams and quizzes are open books, so I encourage you to get good at navigating through this book, because that's how the real world is. You don't just sit there and have all these formulas in your head. You have a reference that you use. You guys have an amazing reference called the internet, which is a great source of information, good and bad. So we're doing inferences about the difference between two population means with sigma unknown, right? That's what we're doing. We're doing interval. So right here, this just says what the margin of error is. But now we need to use t, and as we know, when we have t, we have to do degrees of freedom. And this is our kind of harsh degrees of freedom formula. I am not going to have you use this formula in your quiz. So if you end up feeling like you're using this formula in the quiz, you should stop and think about what you're doing. I'm going to show you how to not ever use this formula in just a second. But for now, I just wanted to do it once. So the way I'm going to do this is that we have a big fraction here. We have a numerator and a denominator. I like making my life easier by splitting those up. So I wrote dfn for numerator. That's just s1 squared over n1 plus s2 squared over n2 squared. So that's going to be equal to, open parentheses, s1 squared divided by n1 plus s2 squared divided by n2, close them, square them. That's what that formula says. S1 squared over n1 plus s2 squared over n2, and then that whole thing squared. So pay attention to parentheses there. That's the numerator. The denominator is next. 1 over n1 minus 1 is 10. Whoa, dude. I think there was just a glitch in the matrix. Now I had to start over, not start over, but start here again because something weird happened to the video right here. It couldn't handle the degrees of freedom numerator. Now, let's do the denominator. So that's where we were at. We just did the numerator. Now we're doing the denominator. So we have this part, right? The bottom of this fraction is the denominator for the degrees of freedom calculation. So that first part says 1 over n1 minus 1. So that's going to equal 1 divided by this number minus 1. I'm just going to type 9 so I don't have to go overkill on the parentheses for this one. 1 over 9, that's 1 over n1 minus 1. s1 squared over n1. So that's this guy again, squared, divided by n1, squared on the outside, plus 1 over n2 minus 1 over the same thing. So now this is going to be 1 over, that minus 1 is 11, times this squared divided by n2 squared on the outside, and that is now the degrees of freedom denominator. So now in this cell, we can just go ahead and divide this guy by this guy, and that's our degrees of freedom. So the book will use 14 in this case, because degrees of freedom have to be an integer. And the book, the conservative thing to do is always to round down. So even though this is closer to 15, the book always rounds down. Now this is where I want to show you, you can avoid using this formula by doing data analysis, and we're not doing a t-test right now, but a t-test result set gives us the stuff, a lot of the stuff we're using in this example. So I'm going to do two sample assuming unequal variances, because this is unpaired data, right? So we know it's not the first one. Generally, you always choose unequal variances unless you have some reason to believe they're very close. So for example, the book might tell you to assume that they're equal, but otherwise you should just use this unequal variances one. So we'll do OK. I actually have the results preloaded in there, so it's just A1 to 11, and then B1 to 13, that's our data. I included the labels, so the title, so I have to click this box. Alpha equals 0.05 is good because we're doing a 95% confidence interval. So 95% plus 5% is 100%. So if we click OK, those results are going to get stored over here. So notice this gives us a lot of the results. The averages 42.5 and 22.3 right there. We already calculated those. It does not do d bar, which is this minus this, right? So that's our estimated difference. So we might write d bar there. It's kind of annoying because that's kind of the main result we're looking at in these tests. But for some reason, they didn't code that into Excel. These are the variances. So notice these are the standard deviations. If I did this equals this squared, 48.728889, 48.728889. So those are the same number. So those are the variances. So you could go back and forth between. Observations, 10 and 12. Hypothesized mean difference, D naught, difference naught is 0. Notice this is why I wanted to show you this. Excel does not use the always round down rule that the book does. So the book will always round down. Now in this example, I did this both ways and the answer is correct both ways because after rounding, you get the same answers, but you should just be aware of that Excel will round to the nearest integer. The book will always round it down. All right? Now we have some t-criticals and stuff there. But let's go here and do the t-critical by hand, and then we could use that to check to make sure we get the right thing. So this is the number. This is our standard error. Now we need to figure out the number of standard errors we need to go. So equals t.inv. 0.975 to the left to get 2.5% in the upper tail. Degrees of freedom now, oops, I forgot my T. Degrees of freedom now, that's why we had to calculate this, right? So 2.14 is how many standard errors we need to go away. Now look at this one. The t-critical two-tail is really this analogous number in these results. So it's a little bit smaller, and that's resulting from this 15 versus 14 issue. So notice that rounds to 2.13. If we wrote 15 right here, that number changes to 2.13. But again, after rounding, it actually doesn't matter. But let's go with the book's version where they use the formula and round down. Now our margin of error, of course, is our number, our standard error times the number we need to go. So 550. Now CI lower is our estimated difference in the middle minus the margin of error. Our upper equals our estimated difference plus our margin of error. And so now we have our confidence interval, 14.7 and 25.7. So I did these other parts in the last video. This is 20.2. Oops, let's just plug them in again real quick. 20.2, 42.5, 22.3, so 42.5, 0, because they want 2 decimals. 22.30. S1 6.98, S2 4.53. Let's see. So now we want to interpret this in terms of the cost. So this is in thousands of dollars. In just dollars, that's 20,200. 95% confidence interval, they want that in dollars too. So this is 14,700. and 25,700. So that is the 95% confidence interval for the difference in tuitions, right? So we're 95% confident that the true difference is in between those two numbers somewhere. Our best guess of the difference is 20,200, but that's a point estimate, right? So then here we use an interval estimate and say like, well, there's uncertainty behind this. But using statistics, we can say there's a 95% chance the true difference in tuitions is somewhere in this range. Well, we should check our work first, maybe. Ooh, sweet, yay! All right, moving on. I'll send you guys this spreadsheet, which I probably already mentioned. Let's go ahead and do Chapter 10, assignment number 9. Adecco Workplace Insights needs a new name. No. Adecco Workplace Insights survey sampled men and women workers and asked if they expected to get a raise or promotion this year. Suppose the survey sampled 200 men and 200 women. If 104 men replied yes and 74 women replied yes, are the results statistically significant in that you can conclude a greater proportion of men are expecting to get a raise or a promotion this year? So greater than, alternative hypothesis, boom, greater than 0. Null hypothesis, less than or equal to 0. What is the sample proportion for men? So 104 yes out of 200. P men right here equals 104 yes divided by 200 total. That's 0.52er. 0.52er. What is the sample proportion for women? 74 women, 200 equals, 74 divided by 200. 0.37er. 0.37er. Let's put it in. 0.37. Use a 0.01 level of significance. So alpha equals 0.01. Let's just put that right here. 0.01. What is the p-value? Round your answer to 4 decimal places. All right, well, we need a bunch of stuff for that. Pooled p. One of the reasons I wanted to show you this one is because you have to use a special formula. Because notice that the null hypothesis says our two proportions are equal. And we build our standard error assuming the null hypothesis is true. So we have to use the special pooled p formula. So if we go to our table of contents, 10, proportions, hypothesis tests, right here they show you the pooled one. Basically what we're going to do is take a weighted average based on sample size as the weights of these two numbers. But since both sample sizes are the same, the weighted average is just the average, but you might have to do a weighted average in some of your problems. Divided by 2. That's just the average, right? I could have just done equals average for those two numbers, but I just typed in the formula for average. So our pooled proportion is 0.445. Oh, d bar right here, we could write equals this minus this, right? That's our estimate of the difference, 15%. Now the standard error of that, we're going to use the pooled estimator right here. So equals square root this number times 1 minus this number divided by 200. That would be like our old school way. If we just were doing one proportion, that would be the standard error, but we're doing 2. So basically we do this again. This times 1 minus this divided by 200. Now, this isn't the way the book shows that formula. They simplify it right here. So they do this. I wrote it this way in Excel. They say, oh yeah, this could be written this way too. I like doing it this way because this is always the way you do it in any case. So I like to just stay consistent, so I only have to remember one formula. but I don't really want you memorizing them anyway. So whatever you like to have, I encourage you to have resources available to you when you do the quizzes and the homework, because that's the way the real world works. People have resources. So z stat equals d bar minus a d naught, which is 0. So I really don't even have to type that. I'm just doing it to make sure you remember. The numerator of a z statistic is your estimate minus the null value. In difference in means and proportions tests, that's almost always 0, so you rarely have to write it. But I'm just writing it here so you guys remember. That's a d naught, the null hypothesis, or the number that divides the null and alternative, right? 0 is the number between the null and alternative hypothesis. So then we divide that by our standard error. P-value equals, so we're doing a one-tailed test looking in the upper tail. So if I just did norm.dist, this number, comma 0, comma 1, comma true, before I push enter, think about what's going to be wrong with that. That seems really big. Well, that's the left. That's to the left of this number. But I want the upper or right tail. So I could do 1 minus to get the opposite. That's the p-value. Another way to do that, because it's a symmetric distribution, put a negative in front of that z-value. That's the left tail, but because it's symmetric, it's the same area. So that's 0.0013, 0.0013. Now, what is our conclusion? So let's look at alpha and our p-value. Our p-value right here is less than alpha. That means we landed in the rejection region, and we will reject the null hypothesis. And so there is a significant difference. I don't like how they wrote this. We really should say it's significantly greater than, because that's what the actual hypotheses are. So they were a little bit sloppy with their interpretation there. But let's cross our fingers and be like, oh, 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 oh. All right. I'll send you guys the spreadsheet. I'll send you guys the notes. I love you guys. I'll see you later.